for K-series stabilizing stable resolutions.
Okay, thank you. Also, I will thank the organizers for giving me the opportunity to speak here. Yeah, my talk will contain 4 parts. So first of all, everything I mentioned will be tried with tangent through unsolved with the previous speaker. So my talk will contain 4 parts. First, background. Then we'll give the definition of. And then I will talk about its action. When it appears in special case what has appeared in the previous talk. And then we'll talk about the twisted algebra, which will be used to give a combinatorial definition of stable basis. Also, one thing I should mention is just to make sure that we know what the object that we are talking about. So basically, you consider X is a symplectic variety, manifold, and with the torus action. So this is usually a discrete set, and you can consider homology theory of this variety and homology of this X. Also, all the cohomology theory that I talk about, K theory, elliptic cohomology are equivalent. Okay, I'm going to say this again. So basically, this is called a stable element. But because this is discrete, so you can take the fundamental class of each individual point and go there. It will give you a class here, and that's called a stable basis. Because I think this name was more frequently mentioned. So I think the motivation, so also the stable basis business comes from Okounkov and his collaborators. After they started this project in 15, 20 years ago, I don't know, on this stable basis. And also after that, some other people worked on this in other special case like Riemannic. There could be a few other names missing. I apologize for that because the list is long. And so I think the motivation, there should be some more deep motivation, but for me, that I can understand is people were trying to consider, like, for instance, the quantum cohomology of elliptic manifolds or quantum K theory. Plus, there should be another quantum, which I believe is not defined yet. Okay. So to define this kind of, to consider this kind of objects, and so you want to study in the morphisms of an object clearly. So to study the morphisms, then people realize, I guess, and many others will realize that you can do the following. That is, so you consider the T fixed points, and you consider the product with the X. Then you can think, take some correspondence. And then this correspondence will give you a map from, just pick H, but you can also replace it by K or elliptic cohomology. So X. So it will induce a map, because this is the stable pendulum. Okay. But of course, this map is not unique, and so you can make, so usually it depends on some choice of chamber in the group of co-characters of the torus T. So for instance, you have one version of the stable envelope, and then you can consider inverse of another version. And this will give you an inversion of this cohomology of yeah. Maybe I should think back. Maybe people were talking about inversion of this XT.
You were saying that your setup is X, the fixed
X
point set is just a finite set, or what do you?
Yes, it's a discrete set.
Finite set.
I think for quiver varieties and the potential bundle of Bragg varieties, they are always finite.
Yeah. I'm not disagreeing. I'm just saying, what other maps do you get besides just push forward? You have this. How does it? Yeah.
In the correspondence.
Yeah. This
basically you have
kind of Z.
you take a task here, go back, and then push forward.
Yeah, but it's just a finite kind of Z you pick?
So for cohomology, certain correspondence here and elliptics to abstract.
I think the construction is a stable envelopes. So this is some
Yeah, I'm not saying that
special.
there's a special correspondence, not some concrete thing.
I don't know what stable envelope is. But
Yeah, of course. That's the, I mean, for cohomology, this was constructed concretely for K theory, and this one is very complicated. Actually. I think, yeah, Okounkov did two constructions, one with logic, and later on, recently in last year, he did another construction here, and which degenerates in this case.
Okay.
But either case is complicated.
Some discussion in the chat about what Z should be. Yes.
Yes, yeah, but not anything. Just some Lagrangian symmetry. Then people realize that this satisfy this R matrix Young vector equations. Actually, they call this R. It's R matrix, and so they satisfy this Young vector equations. So which will such kind of operators will define basically Youngians. And if you look at cohomology, if you look at K theory, it will be common group, and maybe group common group. And of course, if you look at the elliptical version, it will be some kind of elliptic. Yeah, I think it was not defined yet. So then this will be acting on the cohomology of X, and this will be acting on common theory of X. This will be again. Hopefully, it will be acting on some elliptic cohomology of X. So and after that, there are some other structures of these quantum theories. So I think I oversimplify this motivation. Okay. But for me, I will just look at varieties and the numbers. So for me, X equals sigma b. Of course, in Okounkov, there was a special case of potential function of the gross magnitude. Okay. And in that case, this xt projective the wild group. So I'm just talking about this case. And in this case, then you have this stable envelope from, and also I just consider K theory. Similar work was already done for cohomology, and that was by my operator Changlong Zhong. So basically, you have the fundamental class for the point W. So we denote the image to be stable W. Okay. But that's not the definition. That's just some shorthand. And also in this background, in this part, there's another thing related to this stable basis. So because you know that sigma p from topic to given to the potential bundle, so then you have a side to the left. So you have stable basis here, then you will have a class here. And such class will also studied here. Then there's another class actually. So you have stable basis here. Then of course you can define class here. Okay, in for K theory, right here. So for cohomology, this will give you the so-called Chen class, triple right. Okay, that's some class basically mimicking this definition of Chen class. For Chen class is defined only for these smooth subvarieties, and the singular one you don't have the definition, so you modify it, construct using constructible sets, and that's called Chen Schwarz McPherson. And for K theory, it's another class called multi-Dixon class, and using characteristic cycles. That's not related to, I mean, I will not talk about that. But actually mention the names that studied this right-hand side. So, but this side is totally more abstract from abstract geometry. Okay. So now I can start to give the definition of K theory stable basis, but the definition is super complicated and very technical. So I will use the simplified version. So my definition may not be super precise. Okay. So for that, we need to pick some notation first. So T is the torus, and this is the group of vectors. The group of cofactors, and we fix the chamber inside this group of cofactors. So the chamber, fix the chamber. Of course, there's the dominant chamber. You can take any chamber. So, and also we fix an alcove. this Hecke enrichment will give you Changlong and Okounkov. So now so C, if you fix the C, then you fix it a partial order. One group, and similarly, the equivalent say that you fix a Borel subgroup, and then you also have varieties, cells on that subgroup, depending on this Borel subgroup. So then with this, then you can define this attracting set. And you'll see these six have this variety. And this depends on C, so as the C that this is the right. And then of course, you can take the closure, you will get the 4 checking set. Yeah. Yes. It's all depend on C, so that's for the subscript.
What is the notation? This is the potential boundary restrict to the true
Logic on this variety. So that's the first notation that we need to fix. The other one is the degree of a polynomial. So if you have F, combination of these exponentials, so here F mu belongs to. And then you can define the degree of this Laurent polynomial to be the complex of the set mu such that F mu is not equal. So that's a subset of its space. So with this, then one can define the. There's one more thing. It's called polarization, which is an element that will distribution. Okay? But I will not focus on that because in the definition it will play not so important role. So now with the notation, I can give the definition, which actually the theorem, existence and the uniqueness proof of statement of theorem. So you fix a chamber, you fix a polarization, it's alcohol. Then stable envelope is a map going from and finds 3 conditions. So as I mentioned, if you have W, stable of W inside here. And then 3 conditions should be satisfied. And then Okounkov proved that such thing exists and is unique. The first one is called a spot condition. It's saying that stable W. Also, so you can pull back, but you're depending on fixed points, so you can pull back to go to Y group. So then you can just look at its restriction. So this pullback you can denote it by restriction. Okay, and then saying that stable W, the top of this is containing the 4 checking set. W that's the support condition. Part of this class. So the other was
What does it mean for the class?
yeah, because it contains this checking set, right? I guess support means if you pull back to here, then it's almost equal to 0. So Yang was not equal. The restriction is always equal to 0. Unless E is less than equal to W. B and E less than W. Less than equal.
So support is a subset of what? Is it a subset of W or D star of B or where?
If you use this way, it will be just saying that this restriction is equal to 0 unless.
Support is a subset of W.
That's subset of the bundle.
Yeah, the support of a class is not well defined, right? You just want to say the class is supported on a certain subset.
Yeah.
Meaning that maybe it's in the image of the push forward. It restricts to the 0 to the open column.
So second condition is this normalization condition. Okay. We said that stable W restricted W, so it's equal to the normalization by this normalization. So that's why the quotation mark is not exactly that.
Actually, I have a question about this other representation. Quiver.
Yeah, there's a Q. Which one Q? Because I was talking about the C stars here also. Yeah.
Which are from
If the Q is the term of the C star.
Okay.
So that's the second condition. Actually, the first one I was a natural. The second one, depending on what you want, and the last one is more important and more technical. So that's called the degree. That is degree defined here of this table W. Shift that V if V is less than or equal to W. And this may not be equal to 0. Then the degree, which is a convex hull, is contained in degree of table of V, which shift that is another convex hull plus L, which shift that V minus L, which shift that W. Okay, plus means translation, plus minus means translation to the other side. And what's L? L belongs to this alcohol. That's the place where the alcohol plays a role. So actually, if you look at cohomology case, the third condition is much simpler. Actually, it's not a convex hull. It will be just say a polynomial is multiple of another the parameter q in the q. But for K theory, is this one. For elliptic, more complicated. So it turns out that this stable basis is related to this package. And the brief here, fine, this talk mentioned a special case, but which almost. So if you take n tilde, so n tilde is and you have this singular evolution. This is the Stanford right, and you can consider this tilde over n. This is the Stanford right. And of course, you can embed it in n tilde plus n tilde, and you have two projections. And so if you have a class here, you can, so if you have a class here, you can pull back product with this class and then push forward. Okay, that's how you define this action of K of phi. So you can get just T of this time during K theory, and then it acts on this action is performed by this pullback product and then push forward. And this is asymmetric to the half-line Hecke algebra. Okay, and this Hecke algebra is generated by Green together with operators. So here, Pi is called the two-root operators. Two-root, you have a certain operator, and they satisfy operator relation together with the two green. We give you an algebra which is non-primitive Hecke algebra. Okay, so then what we proved was the following. That is, so. Of course, there are so many stable bases depending on the choice. So if you fix this one, so this is the fundamental chamber, this is the continuum bundle, this the anti-dominant alpha. So this one, so this is stable. Then this is actually so over here you have the modulistic operators. So if you have a well group. And you can group element W, you can decompose it into product of simple refractions, and then you have TW, which doesn't depend on the choice of the reduced decomposition. So you can use the TW inverse more precisely, acting on this table. So in other words, all the other stable bases are generated by this one. E is the identity element. Okay. So of course, in this calculation, you have to use the original construction of root stick together with and show that the right-hand side satisfies the three conditions. The last one is the most difficult. Okay. And so I know many of you are not Schubert calculus. So if you know Schubert calculus, you will see that this is one of the most basic basic properties of Schubert class in cohomology and in K theory. That is, so Schubert classes. So the variety is X of W. Class is always generated by operators tau. Inverse the Schubert class for the identifier, which is just a point. Okay, well, this tau is totally similar with this T. It even comes earlier. The operator. And here I didn't say which theory because it doesn't matter. Cohomology or K theory is totally the same. Totally the same. Okay, so that's why it's natural to expect this property. Yeah, let me mention the relation between the two. So this Ti is satisfied the Bragg relation, and then this, if you take the square, it will be 1. Well, this tau I square will be theory. Will be y. Yeah, the Bragg relation is totally similar. Now after this, then what we so-called I call it group algebra. That method, I think, is studied by Constant and Kuma when they were talking about cohomology and K-theory of continuity varieties. Later on, it was generalized by myself with Bashir's Kamis and Ryoda into general-oriented cohomology. And then it turns out that machinery is very helpful, at least to combinatorial computations. This method comes from constant and acoustic research. So that one will be more algebraic or combinatorial. That is, so if you let's fix the notation, which is basically polynomial. Yeah, the wrong polynomial. Okay, and the field of fractions, and then you can define this is the product. Okay, so this is basically just Q cancel it. Okay? So that's a module over Q, and when you want to define product, so the product is treated by the while group action as follows: take an element. So delta W is to denote the basis determined by the W in capital W. Okay, and P is an element in capital Q. So if you want to do the product, it's treated by the while group action because you want to switch the two. So it's P W of P prime, W W prime. Kind of twisted product. Okay. There's a special element corresponding to the identity element, which is called long. Twisted. Now with this, then I can tell you what the materialistic operator is. So Ti in this case can be written down as 1 plus d alpha. So alpha d alpha I divided by 1 e to the negative alpha I. So here, alpha I is a simple root. And that's another way to realize this simplified the constructions from the junction. Get this operator in this non-commutative ring. Okay. Now with this, of course, we need to also consider this QW star. This is denoted by QW. QW star. So QW is a free Q module with rank equal to the order of W, and you can consider it. You consider it as a left Q module because it's and then you can look at its dual and left Q modules. Okay. But if you forget about that, let's look at it because you can consider this set of maps of sets from W to Q, and then you can give a Q structure, Q module structure to this set. Okay. Moreover, this is a commutative ring, which means you can give a commutative product on this set. So here, if you take FW, the basis W maps B to 0 unless B equals to W, canonical definition, and then you product inside here, just take the component-wise product. Okay. And moreover, if you look at this definition, then QW, because QW has a non-commutative product, so you consider homomorphisms of left Q modules, then commutative module theory tells that you still have a right QW action on the set, on this domain, which will give you a left Q module, left action. So QW will act on QW star, and we know Ti belongs here. And it turns out that this actually is more or less anamorphic to KT plus C star of any model localized. So as much as a ring as rings. So with that, then you can take a special class here, let Ti acts on that class, and that will give you stable basis. So before that, let me fix a notation. So elements here are written as sum of BW at W. Well, BW belongs to Q. And actually, if you so BW belongs to Q. So with this, then we can say forward that is stable basis equal to BW inverse acts on this point, this class. So this class alpha. So this is a element in Q, actually in S. And so you just look at this element which only centered or supported on this identity element of vector W. And then you let TWX on this, you will get all the stable bases. Okay, that's the quite combinatorial or algebraic definition of stable bases. So, but that just for this one. If you change the chamber or polarization, then that's a different story.
So Fe itself was part of not being the stable basis.
Fe?
Fe itself.
Yeah, Fe is just a base element for this Q module.
Yeah.
And E is the
It's
identity.
not in the stable basis.
No, it's not. So you can call it the fixed point basis because it's really something. Actually, I need to clarify that this is also isomorphic to HC point. Maybe that's more clear. So I'm really looking at this one, but they are isomorphic. So if you look at stable basis, it's more like on this side. If you look at fixed point basis, it's on this side. So of course, let me mention why we have why do we care about this definition. And there are several reasons. First one is it's simpler. Okay, then you can do computations much easier. So for instance, for at least for people from triple calculus, but I think earthquake geometry, they also always care about like if you have a class and you fix to the fixed point. Okay, with the restriction formula, which is an element in the give a point. So that's called the computation of restriction formulas. Okay, so with this method, it's much easier to do to compute the restriction formulas. Okay, we have a formula which unfortunately is a little complicated because of this quadratic relation. But still, if you want to compute some low rank examples, this will be very efficient. Okay, that's one thing. And actually, an application of this is that we were able to identify so K-theory, and then you can go to this unramified principal theory representation. So basically, that's some representation theory coming from number theory, I think. And so it turns out that on this side you have, so they also have a Hecke first. Okay, you are already Hecke first. And on this side we have this fixed point basis. We have the stable basis. So it turns out that we can identify the left hand side to the right hand side. I think FW goes to the Casimir space. Just a name, I'm not going to tell the detail about it. That's fine, but this one is a little easier. I think it's called the standard basis. Standard basis, I think, is defined by this some orbits of actions of certain group. And so basically, you can have an isomorphism between the two sides, which identifies the two bases here with the two bases here. And with this, on the right hand side, people have some conjecture about the transition matrices. And it turns out that you can, because of this correspondence, you can just study here. So you can use this language to study this side. And some people have already proved some conjecture on the right hand side by using here. That's the second. And now the other thing that is not related to this twisted group algebra, but still related to K-theory stable basis is that so we know these stable basis depend on several things, C, T, alpha. Okay, so you can change these two. That's a little easier. This one is more complicated, so if you change C, then you get. So basically, you are going from one chamber, and then you can go to the next one by crossing a wall. So then you will have wall crossing functors. Okay. This was studied by Okounkov at the beginning, and then we proved that this wall crossing is also related to. Okay, from one wall to the other one, you just apply Hecke algebra, but the indices W will also have to change. Okay, that's called wall crossing. And inspired by this, then we were able to a categorification of stable basis. So roughly speaking, we were able to define, like, for instance, so we defined objects in this category. Okay? And now from here, from C, you can base change to C. And then you can take Rottendy group. Then you will recover stable basis. Okay, that's why it's got some kind of factorification. And the other side, if you base change to K positive, then you will get you will go to this category, certain category of modules over the U of C. And then the stable basis here will go to Lemma model. Okay. That's not a Okounkov and Changlong had a conjecture on for general symplectic methods. Here we have a proof for potential model. Okay. So
Sorry, DB means the models?
yeah, you have to go to B module in the middle of the step by using some localization process.
But this category is D models over T.
No, it's not. Just the derivative.
How do we get universal relative?
Yeah, that's it. You have to go to the this some kind of D module the some D module category, and then take global derived function of global the global sections.
Okay, but what is DBT? What's it?
Just the variety and take the derived category of coherent shifts on the chain complexes of coherent shifts. And
How do you construct the model from the relationship?
this is the through the Okounkov and the Mokovich and the Luminis result on positive characteristic case that you have this. I think it's an incremental difference. After base change, you take here and
Then you use the method.
yeah, right. Use that one. So base change is K, and then use that I'm not familiar with actually, especially the case I think it's complicated. So thank you.
Thank you.